So in practice, what you do, you take this one and you sample regularly. Okay? Now, question. How do I estimate the time of delay? How do I transport the Kramer-Rao bound that I got for a continuous time to the case of discrete time? How can I get the continuous time, how can I get the discrete time Kramer-Rao from the continuous time? Which is the same question that I asked you, and we made it, by transforming the continuous time sinusoid and the corresponding Kramer-Rao for the continuous time onto the discrete case. Now, in order to make that, I make the same reasoning. Now, I'm adding here. So sorry, I was continuing, but since we have these results here, let me use that. Okay. So I'm adding just one page here. How? Let me use the black. How to use the CRB for sample signals. Okay. How can I make it? So essentially, when I say xt equal AGT minus tau plus WT, that is a continuous time. But usually what I do is the following. In my discrete case, my signal is low pass filter, and we can assume that a low pass filter is ideal. So it's an ideal low pass filter at the frequency 1/2 times delta t minus 1/2 times delta t, which is the frequency. The amplitude is 1. Okay? And then this comes out a sampling. So after that I get a sampling, and the sampling frequency is 1/delta t. And so from here I get xn, which is obtained by taking xn times delta t, which is equal to a g n times delta t minus tau plus w n, which is is coming from n times delta t. Okay, so this is the discrete time expression. But look, I have gn times delta t, which is a time, but is reduced to a sample. And then I have a tau. Tau is the time. So here I have a second here is sample position. So in order to put together, I need to transform tau into sample. So this tau can be equivalent to k times delta t. So k is the position of the sample corresponding to the delay. So in other words, it means that if I have my echo here, I'm putting the echo as a triangle. So what I do, this delay is tau, but I'm sampling now. When I sample, okay, so this is xn. So the delay now is not an integer sample. So if tau is equal to k times delta t, k is not integer, is a fraction. Is, k is a 3.72. Okay? It's not integer. So collecting all together, this becomes a g n minus k times delta t. plus Wn. Okay. So my goal is to estimate the fractional sample of the delay. So estimate the delay, the time delay for continuous time becomes estimate the sample, the fractional delay k for discrete time. Now, since I can reduce everything from a continuous time to the discrete time, then I need to be able to transform the Cramer-Hall bound that I found for a continuous time to the Cramer-Hall bound that I get for a discrete time. So, how to do that? It's much more simple than you can imagine. Now, let's consider this formula here. This formula says the variance of tau hat, she is blah blah blah, larger than that. Okay? So I'm simply copying this formula. So let's say the variance of tau hat is larger or equal than, there is a scaling factor, okay, divided by SNR, multiplied by Tg squared. Tg is the duration of the waveform. Okay? How long is the waveform? Now, let's sample that. So if I sample, tau hat, okay, can be transformed into k hat multiplied by delta t in sample. Now, since I'm computing the variance, then what I do, I plug this one in. And what I get is that I have the variance of k hat multiplied by delta t squared is larger or equal than gamma SNR, and then I have Tg squared. Now, continuing, okay? So continuing this, variance of k hat. Now this k hat is sampled. The delay is a 3.22, is whatever, okay? And we will see, if we meet next Wednesday, we will see how it's really computed. Then this one is larger or equal than, now I have a gamma, SNR, then here I have a Tg divided by delta t squared. Now what is this? This one is the duration of the waveform in samples. Okay? I comment in different color. That's the duration sample. So all the problem is transferred to the new problem where everything is described in samples, not in time. So I'm revisiting everything into samples. That's the point. Okay? Now, so that's, I give you the slide so you can meditate a little bit on that. Okay. Now, this is not necessary. Let me say, not mandatory. For a written exam, but useful for homework. Okay? This remark, all these remarks. Now, let's look at another exercise. Now the next one that I was commenting, which is here. Okay. So this one, do you remember we were discussing about that? Okay, so I have a waveform. The waveform is this. And so the first question is compute the energy of the waveform. Okay, so be smart. Find a way to compute. Okay. Now, compute quantitatively the camera bound for the time of delay and evaluate numerically the minimum SNR radio. SNR is defined by 2 times G and A square 0 divided by N0. That corresponds to an RMSE or standard deviation equal to 10 microseconds of the time of delay estimated. Okay, so now how to read this? Please read the text. The text is saying compute the Kramer-Al bound. Okay, so I got the Kramer-Al bound on the top. Okay, compute the Kramer-Al bound and evaluate the minimum SNR. So that means that the Kramer-Al bound, okay, should be smaller or equal because it's the minimum SNR. That corresponds to RMSE. So let's put in our side some reason. What is the MSE? MSE say. What is MSE? MSE is equal to the bias square plus the bias, right? Okay, so if I say the RMSE is the square root for that, okay? Because it's a root mean square error. The mean square error is without the square root, okay? So when I say root mean square error, means that if the bias is 0, that is equal to the square root of the bias, which is equal to the standard deviation. Okay? So that's why I'm saying that, which is the standard deviation, the RMSE or standard deviation is equal to 10 microseconds. So, which means the Kramer-Al bound should be smaller or equal than 10 microsecond to the square. Okay, the square because this is the standard deviation. So, that means that I need to calculate the Kramer-Al bound. But in this case, we know that the problem is decoupled. We know that it's a blah blah. Then this means that the Fisher information matrix on the delay, okay, is equal to 2 times N0. I'm cutting some of the derivation. Then it is A squared integral of G prime T to the square dt. That's the Fisher information matrix element, okay, on the time of delay. So what I need to do, I need to take the waveform and compute the derivative. So I copy. I paste what I need to do, and I go back to the behavior, which is minus TG blah blah. Okay, so the waveform GT is okay. This is TG divided by 2. This is TG divided by 4. This is minus TG divided by 4, and this is TG divided by 2. Amplitude is 1. Okay. So the derivative, this is G. G prime, the derivative, okay, is, so the derivative here is positive, constant. Then the derivative on the other side is negative. And say That's the derivative. Okay? So how much is the derivative? You know, so it's 1 divided by Tg divided by 4. So 4 divided by Tg, the positive. And the negative here is the same, minus 4 divided by Tg. This is the derivative. Okay. So what I need to calculate, g prime to the square, which is, you know, this. Which is 4 divided by Tg to the square. Integrated between minus Tg divided by 2 and Tg divided by 2. So how much is this integral? It is 4 divided by Tg square multiplied by Tg. 2a0 square divided by 0, and then it's equal to 4 Tg square multiplied by Tg. Okay? What was the energy? I did not compute it. Let me see, I probably did it here, because I took it from, where's the energy? Oh, Tg divided by 3. Okay, so energy is Tg divided by 3. So, you know, collecting, okay, that is equal to I tau tau, okay, is equal to, so if I divide by 3 and multiply by 3, this is the energy. Okay. So the Fisher is 6a0 square ag divided by n0, and that is 4tg squared. And so, you know, what was the definition of signal noise ratio? It's 2ag squared here. 2ag a0 divided by n0. So let's take this definition. So it's 16. So it is 2a0 square eg divided by 0 multiplied by 3 times 16 divided by tg squared. So the variance is larger or equal than, so it is tg squared. 16 times 3 is 30, 48. Time 1 over Sn. Okay. So then, you know, if this one has to be, I don't know, 10 microseconds to the square, then I plug in and then I get the minimalized. Okay.
The light formula that you draw was reversed or not? Because in exercise it was
It's the opposite.
the opposite.
Yeah. Doesn't change anything.
No, because there is a square.
Doesn't change anything. Okay. Because when I calculate g prime and then I make it a square. Okay, it's the opposite, right? You know, flipping here and there, I changed the sign. Okay, but now, so you know, answering to these questions is trivial. Okay. Now, the waveform GT can be interpreted as a piecewise approximation of one side of the sinusoid. Now, when you are here, that means that this is the last part of the exercise. So remember, this is not your topic, try to, during the exam, try to skip that part where you don't feel strong. So solve that part where you feel strong and skip where you don't feel strong. That's my suggestion, okay? So now, considering that, so this is telling the waveform can be interpreted as a piecewise approximation of one cycle of sinusoid. So this exercise is saying, now look at the waveform. This waveform, is like a sinusoid. And then, since that one is like a sinusoid with the parameter which is exactly the same, so evaluate if it is better to use a sinusoid or a piece of a sinusoid for time of delay estimation, or this double triangle. Okay? Which one is better? Now, if you need to evaluate which one is better, you need to compare with the same signal-to-noise ratio. So you need to evaluate if, now you have a solution later, so I'm not discussing that. So you evaluate, so you need to recalculate the Kramer-Rao bound. So at the end of the story, you have a Kramer-Rao bound of the waveform A, and you have a Kramer-Rao bound for the waveform B. Okay? So the Kramer-Rao bound for the waveform A means this is the Kramer-Rao bound for the waveform like this. And then this is the Kramer-Rao bound for the waveform this is low. Okay? Which is a piece of the sinusoid. Now, did I draw right? Okay. So now, what I need to write, I need to manipulate my formula until I get something like, I have TG squared, okay? Then I have 1 over SNR, and then I have 1 over SNR. So at the end of the story, I should have the same structure of the formula. But here I have gamma A, one scaling coefficient, and here I have one scaling coefficient gamma B. Okay? Where for the waveform triangle wave, gamma A is, this gamma A is 1 over 48. And gamma B, is something that we need to compute. Okay? So once I get this structure, you see, that's the structure of the formula that I'm indicating. Okay? So this is the Kramer-Rao bound corresponding. Now, my goal is to say which one is better. Which waveform is better. So if I need to decide which waveform is better, I don't stand up because I can't. So, if you need to decide which waveform is better, so what I need to choose is the one that has the Kramer-Rao bound that is lower, right? So at the end of the story, I need to check if gamma A, is larger or smaller than gamma B. That's my goal. So when I say which waveform is better, it's more appropriate, we need to evaluate if gamma A is smaller or larger than gamma B. Okay? Now, let me make it quick and dirty. I'm finishing the time. I would like, I'm you, huh? So I would like to answer this exercise, but the time is running. And I've been spending so much time in making this trick, and so, I have no more time. And I have all the exams to do. But I would like to answer, okay? Can you give me an answer which is reasonable to decide which waveform to choose without making any analytics? You are there, you're sick, but you want to give an answer.
The waveform with the energy more on the high frequencies.
Okay, which one is that? The answer is right. But which one?
In this case, I think
Now,
Sine.
A,
Sine.
huh?
Sine wave.
Sine has a more high frequency content, or triangle. Sharp, right? Sharp is better because since it's sharp, every time you have a corner, small corner, it generates a lot of high frequency. Corners, discontinuities. You know, this one has this discontinuity, then it's finished, smooth, then you know, it's the second discontinuity. Here we have this discontinuity, then another, you know. This is a very, I mean, it contains more high frequency than this. So intuitively, what I suggest you to write, I have no time. You write explicitly. Since I have no time, I have no time to calculate it specifically. But since the waveform A apparently contains more edges than the second waveform, I expect that the first waveform, okay, is, you know, has a Kramerov bound that is lower than the second one. Okay, and then that's it. So you make this intuitive reasoning, you know, for me, is almost as if you did the exercise. Okay? Because you made a logical reasoning. You don't realize, but you are touching some set of logical elements. And from that one, you are giving an answer. Okay. So, by the way, you know, this is taken from an exercise. So, at the end of the story, I mean, we have some analytics of that. Tell me.
Can you repeat why having high frequency content for this to have a better?
Because you know the camera bound depends on the effective bandwidth. Okay, and the effective bandwidth says that the camera bound is much lower if the effective bandwidth is higher. And what is the effective bandwidth? Is simply the integral of the Fourier transform, square of the Fourier transform, multiplied by omega squared. So this omega square is weighting more if the energy content of the signal is non-negligible for high frequency, because I have omega square multiplied by something. So if this omega square, which is, you know, frequency to the square, is multiplied by, you know, by the energy content for high frequency, this is making the effective bandwidth higher and then the Kramerov bound lower. The example of two echoes, you know, you can read yourself. I don't want to spend time. So it's on the book, okay? It's very nice, but I know I have no time to spend on that. Now, I told you I want to discuss about the exercise of the last year. Now, this is the full exam last year. Full exam equivalent of Monday. So, you know, I don't do analytics on that because you have a very nice analytics. I commented the analytics now. Give a sequence of z transform xn equal 1 plus z plus z squared minus z to the cube. With a linear time invariant filter, which is h0 and h minus 1. So this filter is 1 minus z. Okay. Z transform of this filter is 1 minus z. So everything is anti-causal, right? Because I mean, the sequence is anti-causal, the filter is anti-causal. So now, compute the convolution linear with the filter, and now computing this convolution is by the z transform. So it's multiply this by easy. Now, write the structure of the convolution matrix to evaluate y such that it coincide with A, should coincide. Okay. Now, you know, since the sequence is anticausal, then the difficulty of this exercise is to write the convolution matrix to be anticausal. Okay? So the anticausal convolution matrix is simply that. So which is, this is the sequence and this is the sequence shifted. So the anticausal is taking the sequence and shifting up rather than shifting down. That's it. Okay? So, I mean, most of the students realize that they could not understand why to calculate the convolution matrix, but then, I mean, after a while, after sitting, they understood that it was shifting in the opposite direction. Okay? Mostly because the filter was very easy. Okay. This is a solution. It's already, it's global. It's a solution. Now, let's read together. Assume that the sequence X is periodic with is periodic with period 4 samples as indicated by the Z transform in A. Okay, so I have the sequence Xn that is periodic. So it is 1 Z cubic Z minus 3. Then again 1 Z cubic. So it's 1 1 1 minus 1. 1 1 1 minus 1. 1 1 1 minus 1. Okay, that's the period. Repeat the exercise A1 and A2. Now, so the exercise A1 means that the sequence should be periodic, and then the convolution matrix should be cyclic, periodic. That's the exercise A1. Sorry, A2. For A1, I need to notice for A1 that I have a sequence. I remember for solving this, I remember that if I calculate the filtering of a periodic signal, if a tilde is the periodic one, okay, and now filtering a periodic is equivalent to filter the aperiodic one and convolving with the repeater, which is sum of delta n minus k capital N, okay, which is repeating. Okay, so that means that the filtering can be computed by Yn, and now this Yn is from exercise A1. Convolve for a set of samples. Okay. Repeated with the pattern 4. So I repeat by 4. Okay. So since the convolution, is along 5 samples, there is an overlap of 1 sample continuously repeated. Second, I have alpha and beta. Now, in this kind of exercise, like stochastic process and power spectral density, my recommendation is make the block diagram. Now, I usually ask you, like in question A, but if I'm not asking you, do it. Okay. I don't remember if we solved it. Did we solve this? I don't know. But anyway, so make the block diagram. So what is x1? So x1 is alpha n. I'm afraid I did it. I don't know. And here I get x. So you know, x1, looking at x1, this is a moving average. Okay? And you know, since I have a 2, 0 is moving average order 2. Because x1 is obtained by filtering a white, stochastic white process with the filter composed of two zeros. Now, what about x2? x2 is obtained by beta, and then I have x2 n minus 1, x2 n minus 2. Okay, so this one is an autoregressive order 2, because this filter is obtained by taking beta, and you know, I'm filtering with 1 minus 1.2z minus 1 minus 0.7z minus 2. And here I have x2n, which is autoregressive. And what about x3? So x3 is obtained by, again, by taking, an autoregressive, so with respect to x3, and then which is obtained by x1. So you know, we have x1, which is now entering into a filter to get x2. Then, what I do, I'm summing. I sum this with that to get y. So, you know, make a clear representation. Fine. Now, characterize the process x1. Okay, x1, you know, is a moving average. And since x1 is a moving average, I can calculate the autocorrelation by the z transform of the sequence. Characterize x2. x2 here. x2 is autoregressive order 2. And to calculate the autocorrelation is by the Euler-Walker. Okay? Here by z transform. Characterize the process x3. x3 is the cascade of a moving average and the autoregressive. So this one is ARMA. Okay? Because it's a cascade of autoregressive and moving average. Okay? Now, this exercise is asking you evaluate the power of the output of the power. Now, if I ask you to evaluate the output of the power, that means that you need to calculate the autocorrelation around 0 and extract the autocorrelation in 0. Now, since you have an ARMA, you calculate first the autocorrelation for the autoregressive, and then you filter the autocorrelation of the autoregressive with the moving average component. Don't do the opposite because you don't go anywhere. Okay? So for this one is an ARMA. So first the autoregressive part. Okay? Second, the moving average of that, of the autoregressive part. Okay? Now when you make the moving average, you filter the correlation, so the autocorrelation by the you filter these two. To get the power. Last. Characterize the process Y. Now Y is the sum. Is a sum of autoregressive, ARMA. So you know it's very likely that it's ARMA. Actually, in order to exactly evaluate the power spectral density, you need to combine these three blocks. Now, actually, look at this. I have the ARMA component of the sequence x2 and the ARMA component of the sequence x3 that are very similar one another. So probably these two filters, they are the same, they have the same structure. So you can do something on that. Anyway, comes an autoregressive ARMA again. How is the power of y? For alpha equal beta. Okay, so if alpha equal beta means that they are connected. If they are connected, you know, what is the power? Once again, once you calculate the autoregressive component, that's trivial. Sketch the power spectral density for every process in B and C, which means you need to calculate by the position of the zeros and the position of the poles. Last. Derive blah blah, okay, that's for the time of delay. Second, consider the signal of the time of delay, the estimation, the data within the observation window. Then xt is equal to a gt minus tau plus w. The wave from gt is chosen between two possible waves. So the waveform GA and GB, okay, is defined, the waveform, in the corresponding frequency transform. That means that, you know, now this one is the frequency, it's a spectrum, it's not the time. Okay? So in order to apply the conventional formula, we need to remember that G prime in efficient information matrix, recall that G prime square integrated between, you know, of the square of the derivative. Okay, this one is by Parseval equal to omega square G square d omega. That's what I need to remember. So I need to remember that by Parseval, I can either compute it this way or the other way. But you know, since in this specific problem, I don't have the waveform in time, so I need to calculate it the other way, in frequency. Okay? Now, last comment before we go. I need to have from you the list of the formulas. If you don't give me the list of the formula, Monday I don't put anything on the back of the written exam. So last year they gave me this formula, so statistical signal process formula. So this formula chosen by students under their responsibility. So you choose the formula, and I attached on the back of the exam. If you give me no formula, I don't put any formula on the back.
How do you inform
It's you are here. So you I don't know, you have an email, you exchange, you discuss, you do, you blah blah. Okay? You make I mean, he's making a YouTube of everything. So you know, you might have a forum, you might have a Facebook, or you might have something. Okay? Agreed on the formula. Agreed on the formula. I mean, even this one are okay, but I want to receive from you. So I need to receive from you a PDF that I just print together with the text. No PDF, no formula, right? Okay. I need to receive from you 1, 2, so there are in total, like here, 8, no, 10. 10, right. 10 is the number of formulas that you can ask me to put, and I'm going to put.